All right, so the second part of this part of the unit on thermodynamics is going to focus on free energy. And that is basically the net energy change that is present between the changes in enthalpy and entropy in any particular chemical change or physical change that could be used to do work. We represent that with G. That one makes a little bit more sense. It's also called Gibbs free energy. We have to account for the temperature being in Kelvin, since Celsius would allow us to have both positive and negative temperatures. And so we're able to calculate free energy by using this equation here. Delta G is equal to delta H minus T delta S. When we're dealing with it with a degree sign, whether it be delta H or delta S, we're looking at it at standard conditions. So those were the ones we talked about back with enthalpy. 1 atmosphere, 25 degrees Celsius, that your substances are pure, or if they're in solution, they're at 1 molar. When you have a negative value for your delta G, whether it has the degree sign on it or not, your reaction is going to be spontaneous. You're going to be moving from reactants to products. You have not reached equilibrium, and you're going to continue in that forward direction until you reach what we're going to talk about at the bottom. Hopefully, that cop sync sign is going to go away. There we go. When delta G is positive, you aren't spontaneous in that direction. You would be favoring the reactants, and you would require energy to convert those reactants into products. When you have a negative delta G, it eventually is going to use up as much free energy as it can until it reaches a value of 0. And when it reaches that value of 0, it's because you are at equilibrium. So, an example of negative, positive, and 0 that's not as chemistry specific as the ones I'm going to show you right now. Negative would be you using your Chromebook without it being plugged in. The battery is going to run until it uses up all the reactants that are available to it. That's when it's going to reach 0. And if we want to continue to use the Chromebooks, we would have to plug them in and recharge the battery by providing energy to force the reaction to move in the opposite direction. And that would be when delta G is positive. So a way to look at these more qualitatively, you can obviously calculate them, but if your delta G is negative when you're spontaneous, if both the terms in the equation, delta H and T delta S, are able to keep that value negative, then you're always going to be spontaneous. So when you have an exothermic reaction, your delta H is negative. And when you have a increase in entropy, that negative T delta S term will also be negative. And in that particular scenario, when you have a negative enthalpy and a positive entropy, you're always going to be spontaneous. If you go down to the bottom of the chart, if you flip that, when you have a positive enthalpy sign, you're endothermic, you require energy to make that change occur by taking it from the surroundings. And if you've had a reduction in disorder, that would be a negative term. The two negatives would make that positive. You would never be spontaneous in the direction being represented. Your reverse reaction would be the one that is spontaneous. When both terms are positive or negative, your reaction can be spontaneous, but it depends on the temperature. When you're an endothermic reaction, delta H is positive, and your entropy is increasing, that T delta S term would be negative. And since we want delta G to be negative, we want that T delta S term to dominate. And it would do that at higher temperatures. So that's when you would see that be a spontaneous change. If you have an exothermic reaction with a decrease in disorder, a negative delta H, and a negative entropy change, the two negatives on the entropy side would make that term be positive. So you need your reaction to minimize that temperature entropy term, or temperature entropy product, so that the delta H sign, the negative sign of it, will dominate in terms of determining your delta G. So this particular type of reaction would be spontaneous when you're at a lower temperature. Okay, so these are just some examples. If you want to click on the links for the examples, you'll see the actual video clip. This is when you add copper to nitric acid. We saw this in your first chemistry class, and it produces a lot of brown gas, bubbling. The mixture gets very, very hot. So it is an exothermic reaction, so delta H would be negative. If we look at our equation, we have two aqueous solution, sorry, we have a solid and four aqueous solutions on the reactant side. We have one aqueous solution, two gases, and two liquids. So yes, we're reducing the number of aqueous solutions that we have from the left to the right side, but we have converted our solid into an aqueous, and we've taken some of those aqueous solution molecules and turned them into gases and liquids. So this would result in an increase in entropy. And based on what we just saw in the chart, that reaction would always be spontaneous, no matter what the temperature is. And this next one, this is what I did to blow up the gummy bears. Prior to blowing them up, I had to heat up the potassium chlorate, which decomposed into potassium chloride and oxygen. This reaction, because it requires heat to make that decomposition reaction occur, is an endothermic change. And if we look at the two components, or we look at the reactants versus the products, we've gone from being a solid to being a liquid and a gas. And I'm sorry, I don't have that equation balanced for you. You would have two solids on the left, and you would have two liquids on the right, and three gas molecules on the right. So you definitely have an increase in entropy with this particular change. So if we want to minimize the enthalpies term in terms of determining the free energy, we would want to have this occur at a higher temperature, which is when we are able to make this decomposition process occur. But lower temperatures, it would not be as spontaneous. Our next example is the formation of glucose, which is what happens in photosynthesis. And I'm pretty sure that when you've covered photosynthesis previously, you know that there has to be an input of light to make that change occur. So this would be an endothermic reaction. If we look at our reaction mixture, we have six gases on both sides, and we've taken six liquids and turned them into a solid. So we've actually reduced the amount of disorder as we've moved from reactants to products. And so, with this in mind, we've got our endothermic reaction, and we've got our entropy term that is combined with the negative T delta S. So both of these are positive. And so this particular change is not going to be spontaneous at any particular temperature. You would have to have an input of energy in the form of the sunlight to be able, and other molecules that help to produce this, the light and the dark reactions, we're not getting into that right now, to make this process take place. Okay, our final one is nitrogen and hydrogen makes ammonia. This particular reaction, and you'll see this in some of the note examples that we're going to do, actually results in an exothermic enthalpy change. The enthalpy of formation of ammonia is negative. We're going from 4 moles of gases to 2 moles of gases, so we have a positive entropy, sorry, we have a negative entropy change, 4 to 2. We've reduced our numbers of gases. So in this particular scenario, we would want the enthalpy term to dominate. We would want to diminish the entropy term. So we would want to have this happen at lower temperatures in order for this to take place. So it is spontaneous, but we can't do it at higher temperatures. If we do, that's going to cause other reactions to occur than the one we're wanting. So, how can we calculate delta G? We can use the equation that I talked about before. You've got your standard states and your constant temperature in Kelvin that you can get from your table, the one we talked about on the previous video. You can solve for it using a system of equations to find the desired reaction, Hess's law. We did that back in thermochem. And you can use the chart using the moles and the free energy values for your products, summing those together and subtracting them from the moles times the free energy of the reactants when those are combined as well. So we'll do an example of each of those. So I told you we were going to come back to ammonia, and here we are. Um, Free energy follows the same rules as enthalpy. If you are an element in your standard state, you will have no free energy assigned to you because that's how you're naturally found. You're already in that state to begin with. So you would not need an input or an output to form that particular substance. So in this particular equation, it says we're going to use From delta G values in the thermodynamics table, calculate delta H, delta S, and delta G for the following reaction. I'm pretty sure I changed it in your papers and just had you find delta G. Um, so I went and found the ammonia on the chart, and it's 16 - 16.4. Nitrogen and hydrogen are both gases, and they are both in their standard states. So with that in mind, these would both go to 0. And so when I do the math through, after canceling out my units, I get negative 32 kilojoules. I guess this should be negative 32.8. Sorry about that. Okay. Now, yeah, because I didn't ask you, I took out the delta H and delta S part. I didn't want this to drag out too long. So I've given you the delta H and delta S values below. Now you're going to compare your answer to delta G using the equation that we first talked about with free energy, that delta H minus T delta S is equal to Gibbs free energy. So if I take this equation, I want you to notice that delta H is in kilojoules and delta S is in joules. You can't combine kilojoules with joules. You're going to have to make sure you either change them both into kilojoules or both into joules. I'm going to change mine to kilojoules for entropy because you're dealing with pretty large values. So I've taken that negative 199 and divided it by 1,000 to get 0.199. I plugged in my delta H and my entropy and my Kelvin temperature. Again, with the degree sign there, I don't have to give you the temperature. The degree sign indicates it's at 25 degrees. And so when I go through and mathematically solve this through, I get that it too is negative 33 kilojoules. And remember, I said above it should have been negative 32.8, so they are extremely close to one another. And so it really will not matter which way you go about solving a particular problem. You can obviously use your free energies of formation, or you can use the relationship between enthalpy and entropy to get your free energy. So this is an example of a free energy problem with Hess's law. You've got three different equations, and we want to calculate delta G for the equation that's listed there. 6 carbons and 3 hydrogens makes C6H6 benzene. So again, when we did this before, I always try to find my reactants and my products in those equations and get that part set up, and that knowing that the other pieces should take care of themselves. So I want a reaction with carbon, and I see that second one has carbon in it, and I need 6 carbons. So if I multiply the reactants and products in that particular reaction by 6, okay, so that's the reaction. The one in white's what I'm trying to find. The one in blue is the one with carbon, so I'm going to take all of the components of that reaction along with its free energy and multiply it by 6. I'm also going to look for hydrogen. Hydrogen is in the third equation, and I need 3 of them. So if I multiply all of the components of that reaction by 3, I would also multiply the free energy value by 3. Only I want to have the product C6H6, which I have in the first equation, but it's on the opposite side of the equation. And if you remember from when we did this before, remember when we need to flip a reaction, turn the reactants into products or vice versa, the sign of your free energy value is going to work just like it did with enthalpy. It's going to switch as well. So we're going to flip this equation and we're going to divide it by 2 since we only want one C6H6 in our final equation. So there's my flip. I had 12 CO2s, I now have 6. I had 6 H2Os, I now have 3. I have 1 C6H6, which I started with 2. And I have 15 O2s down to 7.5. So that's why you see the negative sign with the free energy, because the equation was reversed. And I had to divide all of the coefficients by a factor of 2 to get the proper proportions. With that in mind, I have my carbon, my hydrogen, and my C6H6. When I canceled out the O2s, you had 6 O2s in that first equation, and you had 3 times a half, which would be 1.5 O2s in the second. On the reactant side, together, that gives us 7.5 molecules of O2. I had the 7.5 molecules of O2 in the product side, so those take care of themselves. And if you keep looking, you're going to see also that the CO2 and the H2O are able to cancel each other out. 6 CO2s on both sides and 3 H2Os on both sides. So that leaves me with what I wanted in my final equation: 6 carbons and 3 hydrogens as reactants, and 1 C6H6 molecule as a product. I multiplied the delta G values for the individual reactions by the factor that I needed to get the equation balanced, and then I added those delta G values together, and that gave me that this particular reaction had a free energy value of 125 kilojoules. So this reaction would require free energy to make it take place. We're going from 6 solids and 3 gases to 1 liquid. Giving up those gases is going to be a pretty significant impact on our free energy value. So that was just talking about how to calculate free energy. Now we're going to kind of see how free energy can relate back to equilibrium. We talked about earlier how delta G is going to be 0 when you are at equilibrium, when you are not moving either towards the reactants or towards the products. So we can use a relationship with delta G to determine that equilibrium constant. Delta G is equal to negative RT natural log of K. When your delta G is 0, then your K is 1. So you're not favoring the reactants or the products. The ratio between the two is the same. When your delta G is negative, you're going to have a K greater than 1 because you're going to be moving towards the products, meaning that you're going to favor the numerator side of that equilibrium constant expression. When your delta G is positive, you're going to have a K less than 1. And that's because if you're a positive free energy, you're favoring the reactants. And so you would have more in the denominator of that equilibrium constant expression. So your K would be less than 1. So for this example, we're looking at it at equilibrium. We're told we have mercury at 1 atmosphere, and we're given its enthalpy of vaporization and its entropy of vaporization. Vaporization being the phase change, and any phase change is in an equilibrium state. This one particular is going between liquid and gas. And we are asked to find the normal boiling point of mercury. So we want to know the temperature at which mercury changes from a liquid to a gas, normal being at 1 atmosphere. So if we take that free energy equation that relates enthalpy to entropy, okay, we know that delta G should be 0, and we want to find what that temperature is when the relationship between enthalpy and entropy allows that free energy value to be 0. So if we rearrange this equation to solve for T, we would add T delta S to both sides and then divide both sides by the entropy equation or the entropy variable, we would get that T is equal to delta H over delta S. And you could do this for um, other pressures than 1 atmosphere. This one just happened to be at standard pressure. Just like we did in that previous example, we need to make sure the units are consistent between enthalpy and entropy. Enthalpy is in kilojoules. Our entropy was in joules. It doesn't matter which one you change, but you need to make them both be the same unit. So when I go through and do the math and I cancel out my units, I get that this temperature is 629.7 Kelvin. And if I wanted it in Celsius, it would be 356.7. It does not matter to me which units you leave it in unless I specify a unit in a problem. So that was one example. Now we're going to solve for K given this particular reaction, and you may recognize that we used this reaction earlier to calculate delta G with. That was the one with negative 32.8, but I'm pretty sure I did the math for this through with negative 32, so I'm sorry. If I know delta G, I want to make sure I'm using my R that is in joules, so that's the 8.314, and I need to make sure my temperature is in Kelvin since my R is going to have units of Kelvin. So if I substitute in everything that I know, I want you to notice with my R, I went ahead and changed it to kilojoules, which meant that I divided it by 1,000. If you want to use joules for your delta G, then you can just use 8.314 for your R. And now I'm going to solve for K. The kelvins are going to cancel out, and I don't want you to stress out about the mole unit with this particular one. I promise it just kind of takes care of itself because that negative 32 kilojoules is like per mole of reaction, which is why the moles disappear. If I go through and do the math, I would not simplify this yet in my calculator. I did it on here just to give you all numbers to look at, but I would probably just carry all the digits through until I got to my final answer. The kilojoules go away, and then to find what K is, I need to get rid of natural log. And the inverse of natural log is that E term, kind of like 10 is the inverse of log or the anti-log of log. So I'm going to take both sides of the equation and raise what's there, um, take E and raise it to what's there. So E to the 12.9 is going to equal E to the natural log of K. The E and the natural log will cancel out. So whatever the value is of K in terms of E to the 12.9 will be my final answer. And I got 4 times 10 to the fifth. Now, how did I come up with 1 sig fig for the K? There was one decimal place with the E. So that was what determined. I think I had 3 sig figs because of what was present on the right side of the equation. And again, it should have been negative 32.8. So it should have kept the 3 sig figs initially. But when you're doing the logs and the natural logs, it's going to be related to your decimal places. Um, so that was how I got the 1 sig fig. Trying to see what else I want to talk to you about. Delta G was negative, which meant that the reaction was spontaneous, and our K is much larger than 1, which also is a good indicator that this reaction favors the products being formed. So I could use this type of relationship between free energy and equilibrium to find out about components that are present in my equilibrium mixture. This particular reaction, we've got SO2 and O2 forming at 2 SO3s. You're told what the equilibrium partial pressures are for O2 and for SO3. It says using the data from the thermodynamics table, figure out the equilibrium partial pressure of SO2. So if I have my relationship, I'm at equilibrium. So I can use that the free energy, the standard free energy is equal to negative RT natural log of K. I can use the thermodynamics table to calculate what delta G is. I know what my R is, and I know my temperature in Kelvin 298, and I should be able to use all of that to solve for what the value of K is going to be for this particular mixture. So I used the values that are provided in my thermodynamics table to calculate delta G, negative 142.0 kilojoules. I can substitute that now into my free energy equation that relates to equilibrium. And when I go through and do the math, I get that 7.8 times 10 to the 24th is my value for K. I wanted to find the actual equilibrium partial pressure of SO2 for this particular mixture. If I know what my value of K is, and I know what the partial pressure is of SO3 and of O2, I should be able to find the partial pressure of SO2 using algebra. So I substitute in everything that I know. Remember that the equilibrium expressions are products over your reactants, and they are raised to their coefficients as long as they are a gas or an aqueous solution. So I went through and substituted in what I knew, and I solved for X, and I got that SO2's concentration was 1.6 times 10 to the negative 7th. Everything we've been doing so far has basically been looking at the equilibrium constant when we're at standard conditions or when we're at equilibrium. Not all the time are we going to be dealing with standard conditions. And so, what we have to remember is that pressure can influence our entropy because it can change our volume. The equilibrium position is basically giving us that minimal free energy value that's available. Anything below that, you would have to add energy to make that change take place. Anything above that, it would be continuing to work. We know that enthalpy has no, as long as you have an open system, you're at constant pressure, is not going to be influenced by pressure changes. But entropy is because of the volume. When you have more space available, you have more potential positions, so you can have a greater amount of entropy present. Smaller pressure, the greater your entropy, since pressure and volume are inversely related. So if we are not at standard conditions, if we are not at 1 atmosphere, we can relate the non-standard free energy to the standard free energy using that equilibrium expression, but we're going to be plugging in what's not at equilibrium, the Q value, as opposed to K. Since if we're not at um, under standard conditions, we are not likely to be at equilibrium. If you were, then you could solve for K, but we will cross that bridge another time. So delta G would be looking at the free energy for gases under any other pressure than 1 atmosphere. The standard delta G would be looking for it at 1 atmosphere. R and T haven't changed, and Q is just based on what quantities, what pressures you have for those particular conditions. So if I wanted to calculate delta G for this reaction between hydrogen sulfide and sulfur dioxide to make sulfur rhombic and water vapor, um, I'm given partial pressures for the three gases. Remember, the solid would not be included in your equilibrium expression. And I'm not making you calculate delta G standard this time. I'm telling you that for this particular reaction, the delta G is negative 90 kilojoules per mole. I should be able to use that equation we just talked about to calculate what the free energy change should be for this particular mixture. I know what my equilibrium expression should look like, that the water should be squared in the numerator since it's on the product side, and the hydrogen sulfide should be squared in the denominator along with the SO2. I've got my delta G value, and I know my R, and I know my temperature. And if I substitute in the quantities that I have for the pressures of those gases, I can calculate what Q should be. If I go through and solve it through mathematically, getting rid of the kelvins, getting rid of the kilojoules and the moles. So that 2.48 is combining the 8.314, the 298, and the natural log of the Q value. We see that this resulted in, or sorry, I didn't include the Q value. We've got the natural log of 9.26 times 10 to the negative 7th. So I keep going, and I see now that when I combine that natural log in, I have had negative 90 minus 34.5. And so this would have had a net free energy of negative 124. So what this is telling me is that this particular system is not yet at equilibrium because we have a very large delta G, that it was greater than what the standard delta G would have been. So it was even more shifted towards the reactants and or it had more reactants present, so this reaction was going to continue to proceed to make more products until it finally reached equilibrium when delta G was 0. Why is all this free energy stuff important? The free energy is what can be used or what allows chemical reactions to be used to provide energy for other processes to occur, like your phones, like your Chromebooks. Um, so when these spontaneous processes occur, you have energy available that can then be used to do stuff. When you're not spontaneous, you don't have the energy available and you need to add energy, you need to add work to your system to be able to allow it to take place. Keep in mind that it doesn't matter what that minimum amount of energy is because you're always going to lose some through evaporation because heat gets changed or lost. Work gets changed into heat in the surroundings. And then we have the entropy change that's constantly increasing in the universe. So these values that we're determining are hypothetical. If you wanted to have a particular reaction occur, you would always want to probably add more energy than what you hypothetically should need to allow that process to occur that would not happen otherwise, because you will always end up needing more energy than what was needed at a minimum due to environmental losses and the entropy changes that we've talked